Thank you so much for being here. I'm Nick Erickson, your host for this webinar. Today I'm joined by Matthew Waite, Dr. Adam Wojcik, and Dr. Peter Bailey, who will be co-presenting today's topic. Before we get started, I just want to take a quick moment to introduce each of our speakers, starting with Matthew Waite. He works for Matelect, a company that designs and manufactures precision scientific instruments. Matthew is primarily responsible for supporting customers in their use of electrical potential drop equipment to measure crack growth and using this experience to inform development. Over many years, he has worked on measuring crack growth under creep, fatigue, and fracture toughness conditions on a wide range of materials. We're also joined by Dr. Adam Wojcik, who is a senior lecturer at University College London. He's also the lead materials consultant for Matelect. Adam has a wide range of experience in both academia and industry, having consulted on setup of calibration labs and headed up research in a wide range of fields. And rounding out our speakers, we have my colleague, Dr. Peter Bailey, who is the principal scientist here at Instron. He supports our technical understanding of test and customer needs in all aspects of fatigue, fracture, and dynamic testing. With a varied background as a materials scientist in both research and industry, he also participates in international standardization, as well as working closely with our customers on more challenging questions. We expect the presentation should take around 50 minutes, and then we'll have some time for questions. I encourage each of you to submit questions as you might have here as we go along. We'll aim to address those at the end. So with that said, I will turn things over to Matthew to get us started.
Thank you, Nicholas, and thank you for everyone who's joined us. Today we're going to be looking at EPD, potential drop, DCPD, and how we can use that to monitor cracks in material specimens. Oops. Slight technical hit.
You should have control there, Matthew.
Brilliant. So there's a brief outline there of how we're going to cover today's work, and brilliant. So electrical potential drop and how it can be used to measure specimens. Like all technology, this is standing on the shoulders of giants. Today's particular giant is Gregor Ohm, who in 1827 defined how electricity flowed through a specimen and then lost his job because the scientific community rejected it. And for the next 10 years, he suffered the indignity of not being understood and also being in a poor employment. But basically, then he was proved to be correct, and they named after him the electrical resistance measurement, the ohm. His definition of potential for electricity is very similar to pressure in a pipe when considering water. And what our technique really follows through is how much we are squeezing that pipe. So we measure voltage and we pass a current through the specimen. There are two definite types of potential drop when we deal with applying this to a specimen to monitor crack growth. There is DCPD, which is simply the flow of the current when it's in a steady state and how that current is affected by the resistance and magnetic properties of the specimen. There's also ACPD, which is an alternating current, and then the magnetic properties push the current to only the surface of the specimen. So they're the two difference, but basically we're looking today at DCPD or EPD. That's where electrical current just flows through the specimen, and we'll consider that as a steady state, and the magnetic effects are minimal. where can we use DCPD? The main place where DCPD can be used is on only conducting materials, but we also need to be able to connect to those. So if the connection is going to cause problems with the potential drop with the test being carried out, it's important to bear that into consideration. A standard CT specimen, there's plenty of low stress areas where you can make a spot weld or a screw fitting, but in other specimens you may well find that there is a uniform stress and the crack is going to not be in a clearly defined place, and therefore possibly PD isn't the right choice in this situation. The DCPD technique requires a 4-point measurement. That's 2 connections onto your specimen to pass electrical current through, and 2 connections to measure the voltage locally to where a defect is developing. Now, as the crack propagates, it changes the resistance of the material and the voltage goes up. The advantage of having those 4 connections mean that the 2 local to the crack development really can pick up a very small change, and therefore we can get highly sensitive values of crack propagation. So this technique has been first really started to be used as electronics improved considerably in the 1940s, and it's been used widely ever since then, particularly in the aerospace industry, with lots of published works through the 1960s, 70s, 80s, 90s, and even today. It is embedded into the standards of testing metals, whether that's creep, fracture toughness, or the most standard one of fatigue. With the changes in technology, so has the technique changed. But the bottom line of this is that you need to have a relatively large current flowing in a specimen to produce a large enough voltage because of the good conductivity of the metal. So quite typically now PD systems use 50 to 10 amps to get a voltage which is stable and reliable, whereas in the past this has been hundreds, if not tens of hundreds of amps to get a sensible value. We use a couple of techniques of pulsing the electrical current, and we'll deal with this a little bit later on, but this basically enables us to keep the specimen cool and get ultra low noise on our specimens. It is totally feasible to get micron level resolution of crack growth with minimal effort. For the last 30 years, we've been working very closely with Instron, and we're now in a place where Instron, although they will support other PD systems, if you're choosing a new system, this is a Matelect system that's recommended. So coming on to some of those techniques that we've introduced into the DCM2 to basically really boost how we keep the noise quiet. And I think we need to look at some of the issues with developing a PD signal. So the first one is, in an ideal situation, to get a large voltage on your specimen, meaning that it's noise-free and easy to read by equipment, you need a very large electrical current. Now, if you go back in the history, some of these have been supplied by big lead acid batteries. In the 1950s, there's reports that people used ex-submarine batteries to develop current in the region of thousands of amps. This would produce a signal quite happily as long as it didn't melt your specimen. As you reduce the voltage, as you reduce the current flowing in your specimen, the amount of voltage developed becomes smaller. And Matelect's equipment supplies just 50 amps. But that means that the voltage which we have is in the order of no bigger than 4.5 millivolts. Now, that's in the same order of magnitude as the voltage you would get from a thermocouple. Now, that then causes problems with PD, with a voltage there which is sitting on your specimen, which you're saying is proportional to crack length, but it's proportional to temperature. Now, the DCM2 removes this this added signal, this noise on your signal, by taking a pulse. So there's no current flowing. We pulse the electrical current on, we wait for it to become a steady state, we then take another reading. And we subtract the reading when there's no current flowing with the reading when there is a current flowing, and therefore the thermal ENF, assuming the specimen hasn't changed its temperature significantly, can be removed. So with doing that, we can now monitor much smaller voltages. But also with that, we have two benefits. One is because we can monitor noise-free a smaller voltage, we can use a smaller current, with that reducing specimen heating. But also, when we are passing the current, the specimen is heating. But when we are not passing the current, if the specimen had heated, it'd be cooling down towards ambient. So we reduce the total energy we're putting into the specimen, and therefore reduce the total heating. There are other effects that also add on instability into the signal for PD. So we know that once a crack has grown in your specimen, as you would need to do to grow your pre-crack or to get a DADN curve, your specimen is opening and closing, at which point there is a possibility that the two freshly broken surfaces will come under contact and electrical current will be able to flow through them, rather than having to take the long way path past into the main bulk, and therefore you could get a change in your reading due to the crack being closed. ASTM 647 says that you need to take these voltage values when the crack is substantially open, either at the peak load or nearby. Now, the DCM2 has the capability of receiving a load input from a test machine and making sure that it takes values and only updates the values on the screen and into the various digital systems it supports when the crack is fully opened, and yet does that in such a way that it produces a low noise signal. While we're talking about crack opening and crack closing, there's other things which are also proportionate to the current state of the crack opening and closing. There's movement of the leads in a magnetic field, and there's also any change in the stress state of the specimen. All of these are compensated for by knowing where you are on the signal, and therefore can get a steady state value for it. Now, coming on to the practicalities of actually connecting this specimen into a real life situation. As we've spoken earlier, we know that we need to make connections onto the specimen, and these connections need to be able to deal with two different criteria. The first one is to be able to get a large current through a low impedance source, because this point here is most likely to heat up if there is any resistance in the chain, because this is where the highest current density would occur. So we recommend high tension, high strength screw fastenings or spot welding of a substantial stud onto the specimen and then bolting down. At some point, we will want to take the data generated from the voltage and generate a value which is proportional to crack length. This means that if we are to have repeatability across tests, these connections to the specimen must be made in a known manner. Throughout the literature, there is also a clearly defined set of equations which can be used to convert this. So some of the famous ones are the Johnson formula and Pickard's, and there's also ASTM note on calibration of a CT specimen. All of these have slightly different approaches on where to connect the current into the specimen and where to pick up the voltages from. This is perfectly okay to use the different techniques, but you must make sure that whichever equation you're using to convert the readings, you use the same wiring arrangement and your specimen is in the same format so that these stay true. Otherwise, your equations do not follow the reality. We also recommend, where possible, particularly if it's a fatigue test, that you independently monitor the crack with either beach marks or something like that, or heat tinting, depending on your particular application. And then when you know those values, you generate your own calibration curve for your particular geometry which you are using. This is the way to get the best possible methodology. For the signal connections, getting highly localized points is also important. Again, screw fasteners can be used. As a general rule, we recommend that the screw fastener has an insulated washer just before the specimen. By doing this, you define the connection point as immediately underneath the screw and not any of the surface which is being crushed against the specimen. So it's only the screw thread which is actually passing the current into the specimen. Also, sorry, the screw thread passing the current into the specimen, and also it's the screw thread which is the point contact for measuring the voltages. I hope just giving a very quick overview on PD has been helpful. We're here to help. I'll take some questions in a few moments, but until then, I think over to you, Peter.
Thank you, Matthew. Sorry, you'll have me back on camera a moment. Hello, I'm back again. Right, so moving on from there, I'm going to talk a little bit about how we come to the situation of oops, that's a little bit soon, of how we actually start using DCPD in materials testing, and taking those raw measurements. And I say raw there with the work from Matelect, they're quite carefully processed, and then making use of that data. In terms of standard, there are various standard tests which use DCPD. And really the standard ones are very much around crack growth or crack extension, if you will. First, and the most obvious one, the most popular use is around fatigue crack growth. So that might be using specimens you'd be familiar with if you work with fracture mechanics. So whether that's a compact tension specimen or a bend specimen or a plate specimen with a notch in the middle. I'll show you an example of that in a moment. The other aspect is when we look at what you might term quasi-static tests, or indeed creep tests, where you're growing and where the crack is extending in a very permanent fashion, but under a static loading, quasi-static loading, I should say. Now, when you look at that family, it particularly becomes of interest at elevated temperature, but I'll talk a little bit more about that in a moment. So why would you use DCPD rather than an extensometer, let's say? Well, first off, as I say, elevated temperature. Why use DCPD? It's too hot. So high temperature tests, as I've noted at the bottom there, in modern times, we do have ways and means of connecting an extensometer to a specimen, maybe reaching into the furnace with the sensing element outside, but we can happily contact the specimen at up to 1200 degrees centigrade. That does not mean that it's necessarily a good idea, especially when you're doing something like a crack growth test, which is going to take some time. You can have issues of the transducer durability, and you can have issues of the contact point. Using the traditional methods for crack growth studies, you have a very sharp knife edge. And when you're at temperature for several hours, if it's very high temperature, then you are going to have some serious issues which you wouldn't worry about at ambient temperature. What else? Next, it's too small. So for many years, certain businesses have wanted to use miniaturized specimens or very small ones. And I think there is a growing interest over the last 5 to perhaps 10 years in doing more with sections of material taken from ex-service parts, if you will. And that does drive you to smaller and smaller specimens. So with that, there are mechanical complications, and it can be quite simply around fitting the extensometer between the loading fixtures. It can be about attaching or machining knife edges, or physically handling. Now, I should now explain that, especially when we're looking at small specimens, and these are radiologically hot specimens. So we're looking at nuclear industry specimens which have been sat inside a reactor and have been taken out. Brief digression. Exposure to radiation, especially hard radiation, can do unpleasant things to your fracture toughness. More learned people than me could explain why. But so one aspect of this is, if we look at this, so I've put up an illustration of actually trying to use a mechanical system with a clip gauge, an extensometer, and a very, very tiny, literally about a matchstick size specimen here. And it is possible, but it's not particularly nice. I can hopefully advance my slide. There we go. So this does come with health warnings, and the same applies whether we're using a mechanical method or an electrical method with EPD. You need some care here, because the crack length relationships are constituted for larger specimens. And there are aspects of, what are you doing to the material? You've got different constraints. But the point is that if we look at tiny specimens, a well-developed procedure for using an EPD technique really can give better performance. And it's not the slightly greater inconveniences are certainly outweighed by the benefits of more reliable and measurement. So the third case, better stability. So this is really a question about concerns during very long duration tests. And so extensometers, so we tend to refer to them as COD gauges, crack opening displacement gauges. or the knife edges on which they sit, they can slip or indeed just completely fall off the specimen. Now, if you've got a well-prepared setup, that should not be the case, but it can happen. And if you have a lengthy test that's going to be running for several days or maybe even weeks, that's an unacceptable risk, shall we say. Now, if you look at the environmental effects of changes in room temperature, both techniques can be susceptible to drift, but as Matthew sort of alluded to earlier, there are various ways that we can build in correction to the raw measurement in DCPD. The other aspect here is, when I talk about stability, is we look at high frequency tests. And although very compact extensometers are available, there are still practical frequency limits, because you have the specimen is oscillating as it's loaded slightly. There's no way it can't, because it's at least elastically stretching. And then you've got another mass on a string hung off it effectively. So they will not always, so they could resonate sympathetically or asympathetically with one another. So once you get past, realistically, I would say about 50 hertz of loading frequency, it becomes very, very difficult to use purely mechanical measurement of that crack. At which point, DCPD, now we are talking about DC measurement here, so you know you are going to be bridging a number of cycles at that point. But overall, it's not actually affected. The mechanical resonance does not affect it. So extensometer versus DCPD, if you haven't guessed already from what I'm saying, what I've said so far, they both have their merits. Both can be viable in most standard tests where you are looking at an extending crack. However, it is important really to stick with one method or the other, because as hard as various people, as I say, much more expert people than myself as well have tried, the results aren't perfectly identical. You will get certain differences. You will see that particularly once we start talking about ductile tearing of materials, and I'll talk about that a little bit in a few minutes. The other aspect is to look into the context of the data usage. So there are times, and I think some of our audience today are working in the aerospace sector, and there are times when, like that, you do have a lot of legacy data, you need to compare with it, and at that point, you have no choice. Even if there is now another method which would be just as good, if not better, you're bound to working with whatever you've used for the last 20 years. So there are aspects which are not purely technical to what your choice might be. So that's a bit about kind of why you would choose to use it. I'm going to now talk a little bit about the two main strands where within Instron dynamic systems we would make use of this, or our customers would. So firstly, fatigue crack growth. So crack growth studies, I'm not going to talk about the whys and the wherefores and the hows here. I'm going to assume that this audience has some idea that there is an interest in the differences in crack growth rate relative to applied stress intensity. So when we come to analyzing the data, we are looking with DCPD analysis, the calculations are ratiometric, and the result is in terms of A over W, so the proportion of the crack length compared to the total width of the specimen. So based on some of the discussions I've heard and I've read about, in principle, you can get theoretically a resolution way down, even below microns, as Matthew said earlier. Although the practicalities might mean I would question that. But the point is, you can get very fine resolution on, once again, very small specimens. One thing you do have to work with here is you always need a reference coordinate. So at some point, you need to know absolutely that you were receiving this voltage result, and you had this physical crack length. Now, when you are doing these calculations live, that means you have to make certain assumptions. So very typically, and Instron software supports this approach, very typically, you would say, this is my notch length. I know I have measured it, I know what it is, and this is my starting voltage. It won't be perfect, but it will allow you to track the crack growth during the test live. And as I put there, the relationship is just a polynomial. Now, a terrible word there, as I'm sure any engineer would say, it's never just anything. You find all sorts of trouble with it. But it can be a polynomial or a circular function relationship. Those can be developed either analytically or by finite element analysis. As long as you can generate a polynomial, you can run it. And with a modern computer, that can be calculated on the fly with every cycle if you really want to. The object of the exercise is, and I've borrowed this little graphic, this little schematic graph from some of the crack growth standard test methods. And you talk about, you can see the force range or the stress intensity is on the vertical axis and the crack length is on the horizontal. So you are aiming for a nice smooth, if you're looking for a threshold stress intensity, the point at which the crack growth with cyclic loading becomes negligible, you want to gradually come down. What realistically happens is for a long while, we would do steps and, do a certain amount of crack growth and step down. The nice thing about calculating pretty much with every cycle and with an update rate of 10 or 20 cycles on your potential drop data, that means that those steps become incredibly small and you can actually achieve a much smoother load shedding behavior. Now, as Matthew mentioned, that really, if you really do want to do this properly and seriously, you should be using at least 3 points, to 3 known crack length points during your test, and correlate those to certain recorded voltages. And it's a way of verifying that your relationship is true. That if it's a basic check to check that the polynomial, the relationship you're using is working properly. Just an example use case, I mentioned aerospace and I mentioned mid-notch tension, or you may sometimes hear them called center crack tension. So this can be a small up to a very large size plate. You can see a very large machine in a small picture on the right-hand side of the slide. And the point is here that you will machine a notch in the center of your plate, and you will allow a crack to grow outwards from each side of that. Now, these tests can take certainly days or up to a week, I believe. Very popularly amongst aerospace structural alloys. And you would commonly, amongst the test protocols I'm aware of, use a sequence of loading blocks. But you still use potential drop to track the crack progress during each block. And you're looking to allow a certain crack extension before you transfer to the next block. So an example of somewhere that you might use it. So that's enough about sort of crack growth. One thing I would emphasize there is that the nice thing in most crack growth studies is that you are looking at, broadly speaking, elastic conditions. So your loading condition for the whole specimen is it is moderately consistent throughout the test. And as Matthew said, there are issues where you can get crack closure and then you would get a contact. But if you synchronize to the loading cycle, then that can all be washed out and dealt with. So the next thing is if we talk about fracture toughness. Now, with a very brittle fracture toughness, measuring crack extension is not usually relevant. There are certain tests which are actually similar to the large plate test I just mentioned, where you do, but the vast majority of tests you will have heard of, ASTM E399, the K1C test. We are assuming a single point and a sudden catastrophic failure. However, once we look at doing more ductile materials, we are starting to look at J1C as a parameter. We're looking at stable tearing, and we need to track that crack extension and then work backwards and find the point where it started to tear stably. So obviously, what you need to do is track the crack growth. Now, in this case, I said that before we were staying nice and elastic. Here, we've got elastic and plastic deformation happening during the test. And that means that we have to do the analysis formally once we've collected the whole test data. And that is, I'm afraid I don't have a specimen to hand, or indeed an image here, I'm afraid. But when you look at a specimen which has been undergone a J1C test, it will often be quite distorted. You will see that it's bent out and that the surfaces of the specimen may be slightly buckled in. So you can see that purely on geometric terms, the shape of the specimen has changed. And you can work out, going back to Ohm's law and resistivity and geometry relationship, you've changed the resistance around the crack as well. So that's not ideal. The other aspect which I am going to mention, but is a far deeper topic, is that you do get stress resistive effects, what you would call piezo resistive effects, and they can affect the measurements. Now, I'm avoiding digging a hole here. We need to focus on actually how we use the data. So sequentially, once you've done your test, you analyze the characteristic features of the test record. Nothing surprising there, but it's slightly different to what you would usually do. Then you would look at you'd look at the correcting the estimated and physical crack length. You need to account for the extension, the compliance, stretch in the load string. Finally, then you can build an R curve and then do your constructions like you would for a mechanically determined an unloading compliance J1C test. If people are interested in that and you're not familiar with these things, that's a conversation for another day, but let's do get in touch and we'll be happy to talk about it. So I mentioned determining reference points. Very briefly, you look for a characteristic change in the slope of the potential drop, and that is deemed to correspond to when you've stopped opening the crack and you've started to tear it. So with ductile materials, we would commonly talk about blunting. So first you elastically open and then you blunt, and the crack tip angle will start to widen, and then you start tearing. So in standardization terms, there are two options for doing this. Either you can compare the voltage with the displacement, or you can compare it with the force. And these do get you two different things. So when you're using displacement, you've no idea what the force is doing, so you end up with one fixed reference point. As illustrated on the schematic on the right-hand side, when you look at the force method, you pick up some of this relationship where there's a slight change in the resistivity with applied force, and you can account for that in your calculations. Just overlaying a couple of real traces. These are the same tests. So this is what I've flip the axes here. I'm sorry about that. You've got displacement on the vertical and voltage on the horizontal, and you look for that knee point in the curve. And then similarly with force, you are looking for the deviation from the linear section. And you can again make out there's a slight slope there. In terms of what we then do to build the R curve, we've got our continuous data for force and displacement and crack length, and we've also got our crack length as well. I've just said that twice, I'm sorry. So we can force those through the equations that are there and written up in the standards. E1820 is probably the most popular one for J1C determination. We then do all sorts of fun things. We plot a sequence of points correlating the J integral with the crack length, and we put together a set of lines and set of fits, and ultimately we come up with something like this, and we make a determination of where the intercept is, and that becomes our characteristic value. Sounds simple, as they say, but anyone who has had to set these things up themselves knows that it's quite a convoluted set of calculations. Now, it's really important here to account for the load string stiffness. So we're doing ductile fracture, and therefore there is a plastic component. So we really are obliged to account for where that plastic displacement is coming from. Now, in order, we've said we can't put an extensometer onto the specimen, so we have to use the displacement of the grips, effectively, or of the actuator. And that means that it should be reasonably linear. But you can see, particularly at the bottom of this plot that I put up, it is a little bit of a curve, and it does make a difference. So I've put up the pointy end of the R curve, the JR curve, and you can see corrected and uncorrected. At a brief glance, you think, oh, they're quite similar. And then you realize that you're looking for an intercept point with one of those construction lines, and the uncorrected value has got additional movement from just the elastic stretch in the pull rods reaching into your furnace, for example. So you have to account for that. Final thing about making comparisons between JR curves. You will get, based on the current state of the art, you will get a slightly different shape to the curve between using DCPD or using an unloading compliance method. There, as yet, no one has come up with a rigid and widely agreed solution for this. I've seen some great work looking at slightly different analytical approaches, which bring them into a much more similar shape. But that's stuff that you can go and look up in various papers and in technical proceedings from ASTM, but it's not yet hitting the standards. Rather shockingly, we seem to be making pretty much perfect time. We've got a short video, which I know that what we almost always get with webinars is people say, oh, I'd like to see a live demonstration, which it tends to be a little bit difficult in a webinar. But what we've got is a short video with an overview of the system and sorry, I'm just trying to do this in the background, and the different elements. And what we're going to do is play that, and we will tell you a little bit about what you're seeing and what's going on. So I'm going to disappear from camera momentarily and set the video to play, I hope. So if you bear with me, there we go. So now you can see we're looking, this is in our applications lab. This is a servo hydraulic machine. and with the whole setup attached, it's got a piston at the bottom there. That's a hydraulic cylinder, which is going to apply the force, in some cases a bearing fatigue force. Then in the middle, you've got the loading fixture. At the top, as I'm now pointing to, there's a load cell. In the middle here, there is an insulator. And I'm just going to pause for a moment and point out that it is important to insulate at least one side of the specimen. Otherwise, as you would probably quite quickly realize, you get a parallel current path going right the way round through the load frame, which wastes some of your useful current. So it's not impossible without the isolator, but it will significantly increase the noise or reduce your signal for the same current. Now I'm going to click play again and let Matthew or Adam.
Hello. Yeah, so just showing the front panel of the instrument. Everything's done from that screen and the knob that you see there, the large dial, and that little knob you press, and you can just kind of cycle your way through the menus. Just the back of the instrument, we're plugging in the current supply. You see very thick cables there, necessary to carry the current and not drop too much power along the cables. That's one of the issues with DCPD. The cables can be quite thick. Signal cables are much thinner, and they go into a preamplifier unit on the right-hand side. They're all NEMO connectors, low noise screened cables. And then you'll see a number of bays which are occupied with different electronics. That's an output. That's where effectively the analog signals come out of the instrument and go into the Instron test controller. We've got a 2-channel instrument, so we've got X, Y, and active reference, if you like, and then a division of that, X over Y, because some equations prefer that X over Y as the input. There is the load cycle, which you mentioned that some people would like to synchronize to the load waveform. You can do that by finding that coming out of your Instron and plugging it in at that point, and we can synchronize to many different types of waveforms and take a reading at peak or indeed at the trough or at the crossover point. We're doing a test here where we're kind of setting up the specimen. We mentioned a number of ways of connecting to it. This is the best way. It's spot welding, as long as you can ensure that you don't damage your specimen in the process and initiate a crack where you don't want one. So this is just the thermocouple welder with a specially adapted head, and we're putting a pin on which is being pre-wired with the voltage wire. So that's a voltage connection, and then the next one goes across diametrically opposed on the other side. That gives you the average DCPD. These are positions recommended by ASTM, and then the reference goes in there. There's 3 connections, but actually there's if you like, there's two measurements. One is common to the other one. The current is going in now. At room temperature, low temperature, you can use screwed connections, and you can deal with very thick cables that way with solder tags. If you're doing high temperature work, then you'd have to go for spot welded connections, beefy spot welder, and that works quite nicely. You can see the fiber washer in there that ensures that the specimen, the current goes into the specimen where you want it rather than elsewhere in a non-discriminate way. Peter's just putting in the specimen now with those pins, and as he said, it needs to be isolated. It's not absolutely necessary, and only one side of it needs to be isolated, and it can be easily done. And then we're back again, starting the test. In essence, all I'm doing there is turning up the current. You can see it going up there. This one's a 50 amp unit. That's pretty high current for a specimen. You don't really need all of that in most specimens, but there you go. We've set it to 50. And then press the button again and cycle through the menu to run, and off you go. And hopefully when we punch that, the signal will start coming through. So X is the active across the notch, and Y is the reference. I think that's it really. I think we've got a shot of the
And what you'll
specimen.
see in just a moment is starting the test.
Yeah.
And you can see that forming there, and then cutting to some while later, just over an hour later, and then again you see the beginning of a J1C test after you've done that pre-cracking, and then a very quick time lapse of doing the J1C test there. So that was it. Just to explain what happens after that, I'm sorry, I shall go to my screen again. That should be good. No, that's not the one I wanted. Marvelous. That's better. That's the one. My apologies. So just so that you see what you build up is during the test, you would see, you would build up a raw data curve, which is, you see force and displacement there. And then you would need to fracture your specimen and look at the start and finish crack lengths and enter those in order to do your analysis properly. This is what I was saying about picking your reference point, your VEL or V0 point, and setting that up. Once you've done that, you create your R curve, and you come up with hopefully a result. So yeah, that's kind of a sense of it. So there's like a whirlwind tour. I think now is a good point to do questions. Various people have already been dropping stuff into the chat. So I will pop back on video as well. Hello again, Matthew. So where are we? So quite early on, go from the top. Quite early on, someone said, do you need to insulate the specimen from the fixture? I spoke to that a little bit. Matthew, Adam, do you want to add anything about kind of how sensitive it is about isolation?
I think it's not that sensitive. It really depends upon your load frame and your specimen size. So if your specimen is a small specimen with a high resistance, then you may well find that the current decides to travel elsewhere if it can. But if it's a typical specimen, you're not going to see much difference when you connect it into the load frame. So there is the requirement in ASTM for testing the resistance at the parallel path, and there is a criteria that you need to meet. And if you've done that, the decision is that the parallel current path isn't going to be significant, and it won't change your reading significantly. However, if you're worried, you just put an insulator in between your grips, and I know Instron can supply those. We've had people in the past use things as simple as a sheet of paper, which not very sophisticated, but it works very well.
Actually. It does work, absolutely. Moving on, and a couple of excellent questions from someone who I know is in the aerospace industry. One is the sensitivity affected by the position of current input and sensor? The answer is definitely yes. There's some interesting work on CT specimens that's been published by Keith Tarnowski. Matthew, I think we've spoken in the past about, you've looked at like doing FEA to look at probe locations and sensitivity.
Yes, there's various things with that. The simple answer, as you've said, Peter, is yes. And there's always a trade-off. You can increase the sensitivity phenomenally by bringing the current in and the voltage pins in, but that's at a risk of your equations being very sensitive to that positioning. So you need to make sure that positioning is absolute if you're going to have comparable equations one for another. A lot of people reduce their sensitivity to improve their repeatability. That's the trade-off there.
Yeah, I mean, there's a form of DCPD called close coupled DCPD, where you bring the current connections in very, very close, as you know, within the limitations of the size of those connections. So you can kind of maximize your resolution. But as Matthew says, there's a trade-off. You improve your sensitivity to cracking. You improve your sensitivity to inaccuracies in the position of your connections. So it's a can be a zero-sum game unless you're very careful. And some people have used traveling microscopes to actually position the connections when they're doing the spot welding, or they create a kind of depression in the specimen so that they can locate the spot welding much more accurately. So these are engineering issues, really. But yes, to answer your question, the sensitivity does vary. There is a lot of literature out there. And if you've got a non-standard specimen, you can always do FEA to discover. It's very simple with DCPD FEA. Just discover where your most sensitive position is and how sensitive you are to putting the connections slightly in the wrong place.
Yeah. Looking down my list of questions, I will just flag up that we're getting fairly close to time. So if we don't get to your question, we will try and close the loop with you by email later on. Someone's mentioned, is this based on Johnson's equation for calibration, or is there a physical measurement post-test? It can be Johnson's. It can be one of the other numerous ones out there. It could be your own one. And generally, in terms of using a physical measurement calibration, that is the best thing to do. In terms of, but obviously you can't do that until you finish the test. So I think best practice would be that you break the specimen completely post-test, and then you back calculate and see whether you're satisfied, or possibly just back calculate anyway. So you live test data has to be based on what a Johnson or whichever module you choose. We can accommodate different ones. For your final report, it is best, you should be looking to validate that against the physical measurements. Interesting one in terms of equipment, though, and I think this is quite, I don't know, very much one for Matthew and Adam. The timing of the pulse when you're looking at synchronizing during fatigue loading. If you have a variable amplitude waveform, can you look at, let's say, picking the peak, synchronizing to the peak, even if the peak is at a different place on one cycle to the next? Presumably, well, fairly slow cycles.
I'll let Matthew answer this, but the answer is yes.
So there's two methodologies here. One is if you're using the DCM2 and you're using our software to gather your data, it will give you a complete set of readings of the average load applied while the reading was taken, average current applied to the specimen while those readings were taken, and the average of the two readings having had all the noise removed. So that will tell you exactly the value of your load when those readings were taken. That's one method, and it just keeps updating and gives you those data points. The other method is we try and synchronize. Now, if your waveform is a continuously varying waveform, it's going to be difficult to synchronize to. We've talked with various people who are doing these sorts of tests about methodologies that we can implement, which include us knowing the flight spectrum you're planning on applying and having particular areas within that data of where we are going to record your values. So it's one of those things where the flight data is known, we can put some intelligent knowledge into it and generate more intelligent outputs. The other option is you can set on the DCM2 a mean level, and then we will just take samples when there has been a peak just above it. Now, it doesn't matter how much above the peak is, as long as it's above that mean level, which it's towards getting sensible, reliable data in these configurations. It's not perfect, but it's a good stab in the right way. I hope that answers whoever's question it was.
I think that's a fair answer, and possibly it's one that we will both follow up with on email, since it is now 1 minute past 2 according to my clock. There are some other good questions. I think quite a few of them are things that are just clarifying from the presentation. The last one that came in was, and I just do want to address this very quickly. There is, are ACPD and DCPD comparable? And the answer is not exactly. And I know Adam will very happily talk to you at length about this. Adam, Matthew, I don't know. I do just want to say, I don't know what you think about this. We'd discussed that possibly we would respectively take on further webinars in future. From the Instron side, we'd probably speak more about the equipment and other aspects of fracture software. Perhaps that Matelect might be thinking about doing something in the vein of ACPD, because that really does merit a webinar in itself.
Yeah.
We're okay. I said we're quite happy to have another webinar, but I suppose just to address the question, they are different, but they are very similar in certain respects. So as long as you understand the nuances between the two techniques, then you can use either. But I think for someone that's never used potential drop before, we would always recommend DC. I mean, Matelect manufacture both AC and DC, so we've got no axe to grind. At the end of the day, we look at the application, we say what's more suitable.
Yep. So I think given the time, we should wrap up there. Nick, I don't know if you want to just sign off and wrap up here.
Yep.
On my side, thank you very much for listening, everyone.
Yep. Thanks, Peter. Before I do wrap things up for everybody, I just have a few quick notes. First, for those questions not addressed live today, like Peter mentioned, we're going to follow up with those individuals by email. Second, we'll also be emailing each of you a copy of today's recording along with a slide deck. And then the last thing I want to mention is we do have a number of other live events coming up like this that I'd encourage you to check out. I'm going to drop a link to our webinar and YouTube live sessions into chat now in case you would like to check those out. So with that said, I just want to say thanks to our presenters from Matelect for joining us today. Really appreciate it. And thanks to all of you for attending. Really appreciate you joining us and hope to see you at the next one.